Assalamu alaikum. Today we'll be doing this question from 960811 October November 17, and we'll be doing part B, which involves assembly language specifically. Right, so here we are given a table that shows part of an instruction set, or for the processor has only one general purpose register, in this case the accumulator, and an index register, which is the IX, right? And we've been given some opcodes, operands, and then opcodes binary and all that stuff, right? So first of all, we'll look at what the question is asking us to do, right? So here we have a trace table for the following assembly language program. We need to complete this trace table, right? So this is our code. This is our code. And this is our trace table, right? And the first part has already been done for us. So first of all, it's saying LDV countdown, right? So what does LDV mean here, right? So first of all, we should be aware of what LDV means. So let's go up and look at what LDV means. So it is relative addressing, and it says move to the address n locations from the address of the current instruction, and then load the contents of this address to the accumulator, right? LDV countdown. So let us look at what countdown is. So countdown is 15, right? So if we start off with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So here we can see that we have indeed went 15 positions down and then loaded this number into the accumulator here, right? And next is that comparing the number with what does CMP stand for here. So if we go ahead again, we can see that the CMP stands for compare the contents of the accumulator with the number n. So in this case, number n is 32. Here we have been given number n, and we're comparing this number with 32, which is indeed not true. And then we have been given JNE and JMP. So here we'll go back again. JNE is when you execute when the compare was a false, and JMP is unconditionally jump to the given address. So here this was false, right? So we move on to carry on. So carry on tells us that we should out character. So at 67, you can see the ASCII code table which states that you are outputting 67 here, right? And then it tells us that we need to decrement the accumulator. First of all, we need to LDD the countdown. So LDD countdown, so specific value of LDD countdown is 15. So first we load 15 here, and then we decrement. DE stands for decrementing the accumulator. So this becomes 14 here, right? Now after decrementing, we are storing this in the countdown. So we will be storing this in the countdown. Here we have stored it, and then we are going to jump to the start of the program, and then we are going to begin from the starting. So here we have LDV countdown again, but in this case we are only traveling. Instead, we are only traveling 14 positions, because on countdown we have been storing 14 now. So apart from this, this becomes 14, and now since we are traveling 14, so we will be in loading 51 to the accumulator, right? And then again we'll be comparing, and the compare will be a false, and then we'll be going to the JNE to the carry on. So when we move on to carry on, we will need to output the character for 51, which is indeed 3. So here we will be outputting 3. Since we have done this, we are going to load this again, and then we will decrement and then store. And now we'll be traveling 13 places. So 13 places leads us to 32, right? In this case, 13 place leads us to 32. This becomes 13. And then we are greeted to 32, right? And now since we are at 32, when we compare this with number 1, then it tells us to jump to finish. Jump to finish tells us to LDM countdown, LDM the number 88. So let us read what LDM stands for here, right? So LDM is immediate addressing. We load the number n to the accumulator, right? So since we are loading the number n to the accumulator, so directly we are loading the number 88 here, right? And then it tells us to out the character. So in this case, 88 stands for X. So we will be outputting X, and that is when your program ends. So this is how you will be attempting this trace table, and you'll be scoring indeed 5 marks here, right? Next, we move on to the program given in part B is to be translated using a two-pass assembler. The program has been copied here for you. The program now starts with a directive that tells the assembler to load the first instruction of the program to address 100, right? And now the question here is, on the first pass of the two pass assembler, the assembler adds the entries to the symbol table. The following symbol table shows the first 11 entries partway through the first pass. The circular labels show in which order the assembler made entries to the symbol table, right? So now we have to explain how the assembler made entries to the to this symbol table, right? So first of all, we need to understand that the assembler scans slash reads the assembly language instructions one line at a time, and if it meets a symbolic address, so if it meets a symbolic address, so it checks if the address exists in the symbol table or not. So if it is not, then it adds it to the symbol table in the symbolic address column, right? So it adds it to the symbolic table. And if it is already in the symbol table, then it checks if the absolute address is known. So if the absolute address is known, then that is entered. The appropriate cell. If it is not known, then it is marked as unknown. Okay, so the assembler software must then complete the second pass building up an executable file, right? So name the second table needed when the assembler software carries out the second pass, right? So for that, you need the instruction table, right? The instruction table, or you could even call it the opcode, right? Okay, so the last part of this question tells us that each of the numbers, the following shows two of the program instructions in the machine code, and this is one of the instruction and this is the other instruction, and then it's talking about what their binary equivalents and the hexadecimal equivalents are, right? So first of all, we need to read that each of these represent complete instruction in 2 bytes. The first byte is for the opcode and the 1 byte for the operand, right? So it's telling us to use the following instruction set to write the numbers for A and B, right? So for out character, it's already been done for us. For J and E carry on, we need to do it ourselves. So J and E here is, I have marked it below here. So we'll be copying this down 1110 0110, right? For carry on, we'll need to move forward and look at here, right? So this address is 104, right? So we're going to change it into binary, right? So for one, okay, so for 104, we need 36, we need 64, 36, and an 8 to make 104. So this is translated into binary here, right? So now we need to translate it into hexadecimal as well. So the easiest trick to do it in hexadecimal is attach 1248 to each of these nibbles. So 4 bits are known as a nibble. So here we can see that this will become 6, 8, 4 is 12, and 13 and 14. So 14 in hexadecimal notation is known as an E, right? And on the other side, you can see it is 6 and it is 8. So our hexadecimal will be E668. So we'll be erasing this because we do not need this anymore. So this will be our use the following instruction set to write the numbers for A and B. A is the binary equivalent of J and E carry on, and B is the hexadecimal equivalent of J and E carry on, which we calculated using binary notation here. So this is for 3 marks, and this marks the end of this question related to assembly.